Hi everybody. I just wanted to do one last video on this inquiry question we've been doing, which was the motion of objects in incline. Now, this is just an extension from all the work that we've done on vectors, applying Newton's laws, and the free body diagrams that we've been working on. So I just wanted to do this lesson, explain some of the, parameters of these problems, and then I wanted to do some problems with you that are in your book. So all this information is basically in your book. I'm just going to go through it to make sure we're all okay with that. So we'll do that. Okay. A couple of things that you need to consider with these problems is this. The objects on an incline no longer have completely, axes which are parallel to the floor. That axis, the x-axis, now tilts with the incline, so therefore it's parallel to the incline surface, and the y-axis now is perpendicular to that incline. The other thing that we need to consider is that every incline is defined by some angle which shows the incline of it. We call it the angle of inclination, and what happens is that angle of inclination plays a very important role, because if you look at this diagram here, the weight vector, the red weight vector here, denoted by the variable fg, no longer falls in our vertical axis. Before, when the object was actually flat on the floor, the weight vector would just pass directly through the y-axis. Here it deviates from that y-axis by a particular angle, and it happens to be that angle is the same angle as the angle of inclination. There's interesting repercussions for this, and what happens is, because that wave vector no longer falls in the axis and it deviates by an angle, that effectively breaks that vector can be broken up into components, and those components have important implications to these problems, which is you get two components which are formed. Obviously, you get your x and your y. If you notice here with objects in that incline, the components, the trig relations change. So normally we're accustomed to having cosine on the x-axis and sine on the y-axis. Here they're flipped around, just on the basis of the nature of the weight vector and how it's deviated. But we can reconcile that. But what we need to understand is that the sine component has the property of being the force which drags the object down the incline, and the cosine component is the one that is responsible for pressing the object against the surface, right? And that's what's happening there. I want to show you guys a quick simulation. Okay, so here we got the simulation, and what we got here is we got all the forces that are acting on this object. Particularly, the purple one is going to be the sine component of the weight vector, and this red value here is going to be a friction force, which acts opposite to the plane. So if we go back to our PowerPoint, we can see that we got our sine component pushing the box down the plane, and we've got a frictional force trying to stop that from happening. So that's what we've got happening here. That red one is going to be our frictional force, the purple one is going to be our sine component, and the blue one is going to be our normal force. Here we can see that the normal force is equal to the weight force, and they're in equilibrium. But what you notice is, as you start increasing the incline, um, the weight force, um, the sliding force, the sine component of the weight force starts to increase. So that means it's getting more influence. But it's being cancelled at this particular instant by the red friction force. So no movement is happening because they're cancelling out. But if you have if you have a look at force axis here, you can see that normal force is starting to decrease. So that pressing force, that's the weight vector, is cosine component that is experiencing against the surface. It's decreasing as the sliding force, the sine component, starts to increase. So I keep on increasing that angle, and it gets to a point where that purple sine component of the weight force intercepts the friction force. At this particular point, this box is in equilibrium. I mean, you could possibly increase the friction force, and therefore that weight force would have to increase. But in this particular instant, where that value is equal to that, they have intercepted, and therefore that object is at its point where it's going to start to slide down, right? So I keep on increasing that that angle of inclination. There you go. The friction force starts to decrease more, and the reason why it's decreasing more is because that pressing force, that the normal force, helped the frictional force be strong, is also decreasing. And that sine component of the weight force keeps on increasing, right? As that angle of inclination, that becomes more prominent, the cosine component, which pressed the object against the surface, decreases. And as that decreases, the normal force decreases. And then as the normal force decreases, so too does the frictional force, because friction depends on the coefficient of friction along with the normal force. So as that normal force decreases, so should that frictional force. And it happens to be that it decreases with increases proportionally with the angle. So I keep on increasing it, and have a look at what happens here. So keep on increasing that force keeps on getting higher and higher with that angle. So I'm nearly at 60 degrees. It gets to a point where I am just on the brink of 90 degrees. And what happens is those force, the normal force, the friction force, they've become negligible. Because once they get to 90 degrees, those forces cease to exist, and that object is effectively in free fall. There's no contact happening between the box and the surface or any significant force. It's just basically in free fall. So there's an elegant relationship between friction, the sine component of the weight vector, the cosine component of the weight vector, and how it relates to the normal force, and how that normal force relates to the frictional force. Okay, and we can sum that up here. So we can use the purple vector as to represent friction. That could be anything. It could be a string tied to the box. It could be the actual friction. It could be air resistance. It could be something. It could be anything. It's anything that's trying to stop the sine component of the wave vector from pulling that box down the ramp. And those are the forces that mitigate the x-axis, and on the y-axis we have the cosine component of the weight force and the normal force, which have to be equating to each other. If they don't, then the object is either flying up or the object is falling through the ramp. So let's have a look at how that is represented here. So let's have a look at the weight, the forces along the y-axis. So they must equal to 0, because if they don't, that means the object is falling through. So since that's the case, the normal force is equal to the cosine component of the weight force. And along the x-axis, we usually assume that there's going to be some kind of motion. That's why when you sum those forces up, you should have a net force. If you don't, that means that the forces are balanced and that the object is static. So in that situation, the forces would add up to 0. But normally, these forces, so whatever frictional force minus the sliding force or the weight force, the sine weight force of the weight vector, usually result in some kind of motion happening down the ramp. Okay. The last thing I wanted to talk about is this. We will go over this in more detail to come, because it's something that does come up, and it's kind of little math tricks that we're expected to know about. So this is a special situation. So what's happening here is, in this situation, the object on the incline is at the brink of sliding. The frictional force has just balanced perfectly with the sine component of the weight vector, and it's in equilibrium right at that point. And that's this particular situation here that we're talking about here. It's just barely maintaining traction. So you can see the forces on the x-axis add up to 0, and the forces on the y-axis also add up to 0. What we can do, because these equations, these two equations that we've derived, relate to each other, we can substitute them into one another, or we can divide each other between themselves, and we can simplify that to come up with an elegant discovery. Okay, and that's what I've gone on to do here. So because the forces are equal to each other, I've noticed that the frictional force along the x-axis has to be equal to the sine component of the weight force, and because the normal force is equal to, the normal force in the y-axis is equal to the weight, the cosine component of the weight force, they're equal to each other. So these equations have simplified to that. So what I can do now is, because these equations are related, I could go two ways about it. I could rearrange one of them and substitute them into one another, or I can divide the two equations by each other, right? And there is a particular reason why I've divided it in this order. Frictional force divided by normal force, and sine weight component divided by the cosine weight component. The reason why I've done that is to simplify and come up with a solution for the coefficient of friction in this object. Now, this isn't a mandatory equation for the syllabus, but it definitely has some working and some intuition that can be extended in other problems, because you will sometimes be expected to derive things, and they're not going to be anything new and novel. It's most of the time stuff that you've learned along the way, and this is kind of like a little bit of an exposure to it. Anyways, I digress. So keep on going, and I've set up the new equation where they're related to each other, where I've divided both equations by one another, and what I can do now is simplify. Fg divided by Fg is equal to 1, so that falls out, and I'm left with sine divided by cosine. Frictional force and normal force proceed into the next step. The thing here that I want you guys to learn is, when you divide the sine trig relation by the cosine trig relation, what happens is that's like saying the tangent of some kind of system that you're measuring. So they're equal to one another, those trig relations. So you can simplify sine divided by cosine to be equal to tan theta. And what I've done now is I've I've substituted the full expression for friction into the other side of the equation. And what happens is, because I have two normal forces on the other side of the equation, I can cancel them out, and I figure out that the coefficient of static friction in this situation is equal to the tangent of the angle of inclination. And that's kind of the elegant aspect that we're looking at there. Okay, I am going to do some, I'm going to do a video on me going through the examples in your booklet. And then I'll get you guys to have a go at those questions in your booklets.